Friends, in continuation to the previous lecture, we will prove that the set Bn dash is Banach space if n dash is also Banach space. What is Banach space? Complete norm linear space. So if n dash is complete, then Bn n dash is also complete metric space. Let us take this result as a theorem. Some part of the theorem we have already proved. Let n and n dash be norm-linear spaces, and Bn dash and Bn dash be the set of all linear and bounded or continuous functions from n to n dash, the function norm from Bn dash to R is defined as norm of T is equal to supremum of norm of Tx, where norm x is less equal to 1. Then following statements are true. Then first, Bn dash is norm linear space, normed linear space. Secondly, if n dash is complete metric space, if n dash is complete means complete metric space, that is n dash is Banach space, then Bn dash is complete, that is Bn dash is also Banach space, is also Banach space. Proof. So in the last lecture we have proved this, that Bn dash is norm linear space. Bn dash is norm linear space. So you refer to the proof which we have seen in the last lecture. Refer to the proof. In the last lecture or in the previous lecture, we have seen this. So I am not going to repeat proof in this lecture. Now second, we want to prove that if n dash is complete metric space. What is complete metric space? A metric space is complete if every Cauchy sequence in it is convergent. So if n dash is complete, then we have to prove that Bn n dash is also complete. That is, if n dash is Banach space, then so is Bn n dash. We have a direct relation here. The completeness of n dash implies the completeness of Bn n dash. So in order to prove that Bn n dash is complete, we begin by taking a Cauchy sequence in Bn n dash. Let Tn be a Cauchy sequence in Bn n dash. We want to prove that Tn is convergent in Bn n dash. We want to prove that Bn n dash is convergent. We want to prove that Tn is convergent in Bn. Prove that Tn is convergent in Bn n dash. So that we can have the conclusion that Bn n dash is complete metric space. If we prove that every Cauchy sequence in Bn n dash is convergent. Okay. Take epsilon greater than 0. By definition of Cauchy sequence, there is a natural number n0, a positive integer n0, a natural number n0, such that if m and n are greater equal to n0, then norm of Tm minus Tn is less than epsilon. Say this is first statement. Okay. If m and n are greater equal to n0, then norm of Tm minus Tn is less than epsilon. By the property which we have proved, we can say that if x belongs to n, x is any vector or point of n, then it is always true that norm of Tm minus Tn x is less equal to norm of Tm minus Tn times norm x. Say this is second statement. So if we observe that this equals to norm of tmx minus tnx, this is nothing but norm of tmx minus tnx, and with reference to first statement, so by combining first and second, we can say that the sequence tnx, see, this is less equal to this, and if we consider the sequence tnx for norm x less equal to 1, then we can say that the sequence tnx is a Cauchy sequence, Note that for fixed point x, this will be a constant. So it will be something like epsilon into norm x or epsilon upon norm x, and we can always make adjustments. So for fixed point, this is constant, that is not going to affect. So that is less than, say, epsilon. You can always make adjustments to this epsilon. Take it as epsilon upon norm x or epsilon into norm x. Whichever adjustments are required, that we can do. So by combining 1 and 2 for fixed point x, we can easily observe that the sequence tnx is a Cauchy sequence in n dash for, and this holds for all points, x in n. By hypothesis, n dash is complete, as n dash is complete, the sequence tnx is convergent in n dash for every x belongs to n. Let us say this converges to some some vector, and this holds for every x belongs to n. So we can define a function. Thus we can have a well-defined function. Thus we have a well-defined function, well-defined as limit is unique. Thus we have a well-defined function t from n to n dash, defined as tx is equal to limit of tnx as n tends to infinity. This is key step of the proof. Tx we are defining as limit of tnx. Now our next claim is that tn converges to t in bn n dash. We claim that tn converges to t in bn n dash. We claim that tn converges to t in Bn n dash. We may need to verify that T is actually in Bn n dash. So that will be a homework for you, a verification part. I am giving you the complete proof here, but some verification can be done by you. In fact, I have provided the verification part in notes as well. So you may refer to the notes. Which verification I am talking about? The fact that T is actually in Bn n dash, that is T is linear and bounded. So that can be easily verified with this definition. That details you may find in the notes which I am providing to you. Anyway, let us prove that Tn converges to T in Bn n dash. Okay. So from first and second, we are using first and second and imposing one additional condition. So from first and second, we could write if m and n are greater or equal to n0 and imposing one additional condition that norm of x is less equal to 1 implies norm of tmx minus tnx is less than epsilon. This follows from the fact that norm of tmx minus tnx is less equal to norm tm minus tn times norm x. Taking limit as n tends to infinity, we get that if m is greater or equal to n0 and norm of x is less equal to 1, then limit n tends to infinity, norm tmx minus tnx is less than epsilon. This implies m is greater or equal to n0 and norm x is less equal to 1 implies I could take limit inside the norm because norm is continuous function. So I could take limit inside norm. Note that we are using the fact that norm is continuous function, which you might be knowing from linear algebra. Norm is continuous function. So this implies m is greater or equal to n0 and norm x is less equal to 1. But what is limit of tnx? Here we have defined tx is equal to limit of tnx. Okay. So this implies that norm of tmx minus tx is less than epsilon if m is greater than n0. Now this epsilon is upper bound for all for the set which consists of these types of elements, these types of numbers, norm tmx minus tx where norm x is less equal to 1. So by using the basic fact from real analysis, least upper bound is less equal to upper bound, or let us say that we are taking supremum. We could write this as, this implies m is greater or equal to n0 implies, now this condition gets removed as we are taking supremum with respect to this condition. So supremum of norm x less equal to 1 of norm tmx minus tx is less than epsilon. This implies m is greater equal to n0 implies supremum of norm tm minus tx is less than epsilon. Supremum is taken over all vectors having norm less equal to 1. This implies m is greater equal to n0. This implies this supremum is nothing but what? It is norm of Tm minus T. So norm of Tm minus T is less than epsilon. And by definition of convergence of sequence, this proves that Tm, this proves that sequence Tm converges to T in Bn n dash. Thus, we proved that every Cauchy sequence in Bn n dash every Cauchy sequence in Bn n dash is convergent. Hence Bn n dash is complete, that is, it is Banach space. Hence Bn n dash is complete, that is Bn n dash is Banach space. Let us define or introduce some notations. Before we introduce these notations, let us recall what is Bn n dash. So first, let n and n dash be, the proof is complete of the previous theorem that you note. Now we are introducing some notations. Let n and n dash be normed linear spaces. We have already defined what is Bn n dash. What is Bn n dash? It is the set of all functions from n to n dash such that T is linear and bounded. Or continuous. The next notation which we are introducing is Bn. It is equal to Bnn, and you can guess what is Bnn. Here n dash is equal to n. So what is Bnn? It is the set of all functions T from n to n such that T is linear and bounded. Or continuous. Third, we are defining n dash as Bn R or maybe C, depending on whether n is real or complex valued non-linear function. So for the sake of simplicity, let me take R here, but you note that it can be C or R depending on whether n is real or complex non-linear space. And again, this will be equal to set of all functions from n to R or C such that T is linear and bounded. Note that R is also non-linear space over itself. Over itself means over the field of real numbers, and same is true for set of complex numbers. So n star is Bn R or Bn C. Finally, we define n star star as Bn star R. Fourth, we define n star as B n star star as Bn star R, and it will consist of all functions T from n star to R such that T is linear and bounded. T is linear and bounded. Okay. So we have seen these four notations. Remember, Pn n dash, set of all linear and bounded functions from n to n dash. Bn is set of all linear and bounded functions from n to itself. N star consists of all linear and bounded functions which are scalar valued, that is either real or complex. So you may replace R by C as well, depending on whether n is real non-linear space or complex non-linear space. We will see two more definitions in this regard or in continuation. So first definition is, let n and n dash be non-linear spaces. Let n and n dash be non-linear spaces. A function T from n to n dash is called isometric isomorphism if first condition T is linear, second T is bounded, and third condition T is 1 1. T is 1 1. So this is isometric isomorphism of n into n dash. Isomorphism, to be precise, I'll say isomorphism of n into n dash, T may not be onto here. This is simply a isometric isomorphism of n into n dash. I missed a condition, an important condition which I'll add. Fourth, that norm of Tx must be equal to norm of x. In fact, this fact implies that it is 1 1. So one of the conditions is redundant, but let me keep all 4 conditions here. Norm of Tx is equal to norm of x for all x belongs to n. Next definition, I am going to modify it here only. Let n and n dash be non-linear spaces if there is a function t from n to n dash such that if there is a function t from n to n dash such that t is linear, t is bounded, t is 1 1, norm of Tx is equal to norm of x for all x belongs to n, and finally t is surjective, that is t is onto, t is surjective, that is onto, t is injective as well as onto, then n is said to be isometrically isomorphic to n dash. Note that there will be slight variation in some of the definitions in different references that you can find on functional analysis. I am trying to stick with our textbook for notations and definition purpose. So by isometric isomorphism of n with n dash, we mean an existence of function t from n to n dash satisfying all 4 properties. Finally, I'll conclude this lecture by taking an example. So this example is about convergence of compositions. Let me refer to the textbook for this example. I'll check. So this example, you can find it on the page number 222 in our textbook. This is the example on convergence. Let Tn and Tn dash be sequences in Bn n dash, the sequences in be sequences in Bn. What is Bn? Recall, we have defined this notation. Bn is Bnn, that is set of all linear and bounded functions from n to n. Let Tn and Tn dash be sequences in Bn equal to Bn n dash which converge to which converge to T and T dash respectively. Prove that Tn Tn dash converges to Tt dash in Bn. Answer or proof of this statement. Let me state that Tn Tn dash denotes the composition. It is not the product. In fact, product is undefined. It is Tn composition Tn dash, and Tt dash also denotes the composition. T composition T dash. Okay. So this basic thing you take into account, and all are functions from n to n which are linear and bounded. So by using some simple argument which you are familiar with, we can easily prove this. Let me prove it. Before I write the precise proof, let me explain you the idea of the proof. These are convergent sequences, and we want to establish the fact that convergence is preserved under the composition. Okay. So in order to establish this, let me do some rough work. Norm of Tn Tn dash, I would like to make it as small as possible, less than epsilon, and with some adjustments I could make it norm of Tn Tn dash minus, say, T Tn dash plus T Tn dash minus T dash. So I am adding and subtracting this term Tn dash, and this will be less equal to norm of Tn minus T, norm of Tn dash plus norm of T, norm of Tn dash minus T dash. Okay. Now using the fact that this function is convergent, this sequence is convergent. You know from the theory of metric spaces that any convergent sequence is bounded. So this is going to be bounded, and by using bound of sequence Tn dash, I could make it less than, say, epsilon by 2 somehow by using the bound m of Tn dash, and by using the fact that Tn dash converges to T, I could make it again less than epsilon by 2, and this whole expression would be less than epsilon then, which equals to epsilon. It will be less than epsilon, whole expression. So this is the idea of the proof. You are already familiar with these types of arguments in algebra of limits. So same idea we are going to prove. For the sake of completeness, let me give you a detailed proof of this. Let epsilon be greater than 0, since the sequence Tn dash is convergent. In fact, what is given? It converges to T dash. Is convergent in Bn. It is bounded. It is bounded. Okay. Since Tn dash is convergent in Bn, it is bounded. So there is constant m, positive constant m, such that norm of Tn dash is less equal to m for all n. Let us call this as first statement, which will need for all n, means for all positive integers n, or for all terms of the sequence Tn dash. This is first statement. Now we will make adjustments. As Tn converges to T and Tn dash converges to T dash in Bn, there are positive integers n1 and n2. There are positive integers n1 and n2 such that if n is greater equal to n1, then norm of Tn minus T is less than epsilon by 2m. Epsilon by 2m. We have already done rough work, so you can get why we are having this choice of epsilon by 2m. So this is second statement, and n2 such that if n is greater equal to n2, then distance between Tn dash and Tn dash and T will be less than epsilon upon 2 times norm T, but we need to take care of the fact that norm T may be 0. So I'll add some positive constant, say 1. So epsilon upon 2 times norm of T plus 1. So this is our statement number 3rd. Take small n as maximum of n1 and n2. Take n is equal to, you are very much familiar with these types of arguments, and this is second level course of on analysis or say algebra. So I'm not going to explain each and every step in fine detail. You can easily understand whatever arguments I'm discussing here. So take n is equal to maximum of n1 and n2. Then from first, second and third, we will have this argument from first, second and third. We will have, if n is greater equal to, better let me take the maximum as n0. Let me denote the maximum of n1 and n2 by n0. Then from first, second and third, if n is greater equal to n0, we can observe that norm of Tn dash minus tt dash is less equal to norm of tn dash minus, if possible, try to rewind the video and have a look at the rough work which we have done. Norm of, so I want to make tn minus t to be less than epsilon of t dash. So I'll add and subtract the term here t dash, I mean tn dash plus, I'm adding and subtracting the term tn dash minus tt dash. This is less than, this is less equal to norm of tn minus t, norm of tn dash plus norm of t times norm of tn dash minus t dash. Note that we are also using a basic fact here, norm of AB, where A and B are any linear transformations from n to n, is less equal to norm of A into norm of B. Okay. So with these observations, this evaluates or this simplifies from first, second and third. Combine all the facts, you will get that epsilon by 2m into m plus norm of t upon epsilon upon 2 times norm of t plus 1. Here we are using second and third. This is equal to epsilon by 2 plus epsilon by 2. We have norm of t upon norm of t plus 1. Since this is always less than 1, this will be less than epsilon by 2 plus epsilon by 2, and this equals to epsilon. So thus what we proved, if you want a reason for this step as well, you may mention, since norm of t upon norm of t plus 1 is always less than 1. So thus what we proved, if n is greater or equal to n0, then distance between tn dash minus tt dash is less than epsilon, and by definition of convergent sequence, this proves that tn dash converges to tt dash in Bn. This proves our required conclusion. Thank you.